Hi, my name is Refiz Duro, and I'm working as a scientist for Austrian Institute of Technology in Vienna. The title of this e-poster is Detecting Moving Vehicles in Very High-Resolution Satellite Imagery for Monitoring Dynamics of Air Pollution Sources. This is a well-known problem. Air pollution causes deaths, causes health problems, and so on. So one of the research objects is really the cars, as we want really to tackle this kind of and monitor this source of pollution. It produces carbon monoxide, nitrogen oxides, particulate matter. So monitoring it as an emission source would really help planning and actually also responding to certain levels of air pollution. So monitoring air pollution has, of course, different methods applied in general. So usually using fixed ground air quality sensor, satellite data, monitoring emission sources, having included data models and so on. But of course, some of them lack on spatial resolution, temporal resolution, but as well as accuracy. Our methodology is built around the simple formula. So distance is speed multiplied by time. So if you want to detect a moving object, you need information on the object location from two different points in time. If it moves, its position will change. So, and then it's possible to establish its speed using this particular formula. However, in satellite images or generally in satellite missions, it takes a lot of time. So revisit time is quite, let's say, limited, meaning that you will image one location or revisit one location with minimal 1 day in between. So time, what we do here is exploit the time lag intrinsically built into the design of some selected satellite missions. So this time will generally be quite small, making it possible to use this formula to detect moving objects. So we're talking about worldview missions, worldview 2, worldview 3, and so on. The table here shows you these different bands, and we exploit this time lag after the start, what you see in the third column here, between the imaging in these different bands to exactly address this problem. So on the right-hand side here, you see the image, or actually the composition of a couple of images in different bands showing the movement or really showing the movement of the objects, so on. So we are applying principal component analysis with pixel value thresholding, of course, mainly applied specifically applied on the multispectral images, these 8 bands. But just for the purpose of presenting the results here, we are choosing the panchromatic image here on the left-hand side to show you that this is a city with a lot of traffic activity. We have a certain some area we focus on, and the third image you actually see the result, the output of this principal component analysis, which produces an output image in which neighboring dark and bright polygons are visible. And these dark and bright polygons, these pairs, are an indication of a moving vehicle. So the detected moving vehicles are marked green tags here. This is like the output and the result of this. So principal component analysis combined with the pixel value thresholding produces this output on the right-hand side image. This is urban area, but this is also applicable to a rural area, which you can see here on those image below. Challenge with thresholding is that you have to play around with it. So in this particular case, you see in the upper corner, upper right, left corner, you see low thresholding producing a lot of spurious detections, and then after some change on the limitations, you see a result on the right bottom side, which is quite clean. Next steps would be to apply this methodology together with some data on the cars. So their car types, their levels of emission and certain gases and so on, to establish some levels, but also to simulations, as well as to apply this methodology to a new constellation of satellite images, Worldview Legion, which could initialize near real-time monitoring possibilities.